having some trouble with the camera and so forth. Anyhow, we were cut off. We're going to come back here. Here we have our sphere full of water, central ray, and so forth. Now I think we were into the close-up. We have the central ray and a ray coming in parallel to the central ray at distance delta x. We see the labeling delta x. We have the angle of incidence theta sub I, which is the angle with a radial line, because this parallel ray is coming in and essentially striking the spherical surface along a tangent to the surface, okay, at this angle. So the theta I, the angle with normal, is our angle of incidence. We have an angle of refraction, which is going to be smaller than the angle of incidence. Since the index of refraction here is 1.33, we got that up a little high. But since light is moving more slowly here than here, we're going to bend the ray toward the central ray in this case, toward the normal line, and therefore, because of the configuration here, toward the central ray. And we're going to try to determine exactly where this thing crosses the central ray, assuming that it doesn't, that it crosses inside the sphere. It's going to turn out that for 1.33 index of refraction, it doesn't stay inside the sphere, and we've observed that anyway. The center of the circle is here. We have the radius r, and we have Snell's law for this refraction here that says the sine of the incident angle over sine of the refracted angle is 1.33 over 1, or just 1.33. And remember that the index of refraction is here inside the material where the index is 1.33. The index goes here, the angle goes here, because we have this inverse proportion that we've already talked about and also observed and worked with. Now, what are the implications of this figure? Now, let's work through the mathematical details of what goes on. Here we have the same figure. Here's the center and the radial line, the angle of incidence here, the delta x distance between the two parallel rays here. We want to determine the angle theta sub I in terms of delta x and the radius of the sphere. Now, I haven't written the radius down because there's enough labeling here, but the radius we're going to call capital R. This ray is parallel to the central ray by assumption, so that this radial line here, from which we're measuring the angle of incidence and the angle of refraction, is the transversal of the two parallel lines. Therefore, the angle theta I here is the same as the angle here. Now, for small delta x, which is all we're talking about here, for large delta x, everything gets much more complicated, and we're not really interested much in it unless we're into correcting for spherical aberrations and stuff, which is beyond the scope of most of what we do in this course. We determine this angle theta I by looking at this triangle here. Now, this triangle has a hypotenuse which is equal to r, and it has delta x here. And then there's some unknown side here, which will of course be r square root of r squared minus delta x squared. But delta x is small. Now, for small delta x, we know that the angle in radians is approximately equal to its sine. What's the sine of this angle? The sine of theta sub I is the opposite side over the hypotenuse, which is delta x over r. The angle is about equal to its sine, so the angle is also approximately delta x over r. So we say that theta I is approximately delta x over r. The sine of theta I is approximately delta x over r. Actually, sine of theta I is delta x over r. That's not even an approximate, but the angle is approximately delta x over r. This is a very good approximation when delta x is a lot smaller than r. For delta x down to 1/10 of r, even down to 2/10 of r, the approximation is good to within 1 or 2%. Okay, so we know the angle theta sub I. In radians, it's delta x over r. Then what's theta sub r? Well, theta sub r over theta, sine of theta sub r over sine of theta sub I is 1 over 1.33. That's just the reciprocal of the relationship we saw on the other page. Since we're solving for theta r, we wanted to put it in the numerator. So that sine of theta sub r is sine of theta sub I over 1.33. What's sine of theta sub I? Well, it's delta x over r. So sine of theta sub r is delta x over 1.33 r. And it follows then that theta sub r is approximately equal to its sine, delta x over 1.33 r. So now we've determined the incident and the refracted angle, and now we're going to do a little triangle trigonometry to determine where this refracted ray meets this central ray. We know enough about the angles to set up a triangle that we can solve and determine these quantities.